Okay, so for the final act of acid-base titrations in this class of Chem 108, we're going to talk about the titration of a weak acid that has more than one titratable proton. We call these polyprotics before, so that came as the generic term of H2A. And so I'm just being really clear here and writing out all the possible reactions that would take place in a problem like this. And in the previous problems, we only had one proton. And so we really had two different reactions that would occur. We had a neutralization reaction, which would have been the first one, and we would have had one dissociation reaction, which would be the same thing as it reacts with water instead of the strong base. But now, because we have H2A, we have the first neutralization and then the second one, which is the second proton, and the same is true for dissociation. We have H2A dissociating water, and then we have HA dissociating water. So there's four equilibrium conditions here to think about. And the titration curve is just going to add one more bump. So in the monoprotic systems that we talked about before, we would start at 0 and we would have the first titratable proton. We'd have a buffer region right here. So this would be our buffer region. And we would hit equivalence when we added exactly enough base that we got rid of all the weak acid. And then we had this sort of unique condition where right in that flat region, in the buffer region, where there was pretty inconsequential pH as we added more of the base, that's when pH is equal to pKa. But now when we have two titratable protons, we essentially repeat this again, but for the second pKa. So we have our first buffer region where pH is equal to pKa right in the middle of that. Then we have our first equivalence, and then we have our second series of reactions where pH is equal to pKa2 right in the halfway point. We call this buffer region 2. So we'll just say buffer 2, this is buffer 1, and then we have a second equivalence point, which is when you've added enough volume to totally remove the second version of that acid, and then everything beyond that is excess base that we have in the system. And just like we alluded to before, this halfway point where pH is equal to pKa1, that's halfway to equivalence. That's when you've added exactly half of the strong base to convert half of the H2A to HA. That means at the system equilibrium, you'd have equal parts of these two things, which we know from the Henderson-Hasselbalch equation, that then that latter term falls off and pH is equal to pKa. That happens at half the equivalence point. And then similarly, the pH is equal to pKa2 at halfway to the second equivalence point. And what hopefully is natural that falls out of this is that the volume equivalence for 2 has to be double the equivalence for volume 1. Because if you start with, say, 1 mole of H2A and you completely titrate it to the first equivalence point, that means you now have 1 mole of HA minus, which means that you need still the same volume to convert it all the way to the final form of A2A minus. And so this looks complicated, but actually a lot of these are derivable simply through deduction. So let's see if we can use that deduction and come up with a really rough sketch of where we would expect these major points to be on a curve for just a generic diprotic acid like H2A being titrated with strong base, where we know the two pKa's. So let's see if we can just figure out where the first and second equivalence points would be. That'll help us understand where we are in space, and then we will figure out where pH is equal to pK1 and pKa2. So for the first equivalence point, we are saying how much NaOH is needed to add to the H2A to completely drive the first reaction. And so we'll pretend that we have 100 mils of 0.1 molar H2A, and we're titrating with 0.1 molar NaOH just to make sure our numbers are really nice and clean. And what we're talking about for the first equivalence is fully titrating the H2A so that we've converted 100% of it to HA. So what's that volume? Well, it's no different than what we did for a weak acid when it was monoprotic. So we're essentially just treating this first step as if it were a monoprotic acid, and in which case we just used M1V1. So popping that into an expression then gives us that we would need to add 100 mils of this titrant NaOH to completely titrate H2A to HA in the solution. So that would be our first equivalence volume. And so I'm going to mark that here because that makes it really helpful for us to understand how we should go about solving any other parts of this system. And so we know that everything in this region is going to be a buffer zone, which we could solve with the Henderson-Hasselbalch equation using the first pKa 1. We also, through deduction, could say, well, if it took 100 mils to convert all of the H2A to HA, then it must take another 100 milliliters to convert all of the HA to A2 minus. And that's always going to be true. It's always going to take 2 times whatever the initial volume was, volume for equivalence 1, to get to the second equivalence, because you're not adding or removing any of those moles. You're just simply converting them from one form to the next. So we start with everything in the form of H2A, and then we convert it to everything in the form of HA, which then at the next titration, we take the same amount of HA, which we started with, and convert that. And so now we can draw a second line here, which would be 200 mils for our VEQ2. And in that region, which is our second buffer zone between the first equivalence and the second equivalence, then we would also use a Henderson-Hasselbalch equation, but now we would use pKa2 because what we have in solution here is a mixture of A2 minus and HA. So just to be clear, I'm writing that up here. So in this first buffer zone, we have a mixture of H2A. So like right at 0, we have pure H2A. And right here at 100, we've converted it all to HA. And everything in the middle is a mixture of both, which means we can just use the Henderson-Hasselbalch equation with that first pKa that pertains to that dissociation to solve what the pH is. Similarly, once we've converted all that H2A to HA minus, now we enter this new buffer zone where we have a mixture of these 2 other acids and conjugate base, but it just becomes the same problem. It's still Henderson-Hasselbalch, where the pH is governed by the ratio of these 2 things, but now we use pKa2 for the dissociation of HA minus. And then everything out beyond the second equivalence is calculated in the same way that we dealt with before, because now you just have a bunch of excess strong base that dominates the pH of the system. So you just figure out how much excess you have and use that to determine the pH. Very similarly, this point at 0 is determined exactly the same way as the monoprotic case. You would start with H2A, you'd say how much of it dissociates in water, and what's that initial pH, and that would set our initial point. So for that first condition at 0 milliliters right here, then we're really just treating H2A as if it were a monoprotic system. And we're saying, well, that has a much higher Ka than the second dissociation reaction, right? Because this is a logarithmic scale, pKa of 2 versus a pKa of almost 10. That's about 8 orders of magnitude difference. So we're talking about like 10 to 100 million times more acidic, this first one. So that's sort of the approximation we're making, is it really is just behaving like a monoprotic, in which case it's sort of old hat for you. You know exactly how to set this up. Dissociates by some factor X, we solve that, and we get the pH of 1.18 to start. And in this buffer region, then everything is identical. So I'm not going to walk through that step because it's identical to the monoprotic system. You would set it up and write out to figure out how much of each of these 2 things you have in the system. Use Henderson-Hasselbalch with pKa1, and you would end up being able to calculate any point on this line within this region using exactly the same techniques you've used before, until you get to, of course, the equivalence point. And remember, a really nice thing that you can toss up there without really even thinking about it is, what is the condition when these 2 things are equal to each other, H2A and HA minus? Well, that's the condition where pH is equal to pKa, and that's right dead halfway in this buffer region, and we know pKa1 is 2.34. So we know this point in space without even doing any math. All we needed was pKa, and we knew that that is what it's going to take. And at what volume? Well, it's always going to be half the volume of your first equivalence. So if we knew the equivalence was 100, then this condition will occur at exactly the addition of 50 milliliters, because that means now you have half of each. And we can finish this line using the same logic. We know that this is going to increase very quickly when it's outside of the buffer zone, so it looks like this. And then it's going to flatten out a little bit again. That's the second buffer zone, and then it's going to ramp up again. And we know this point as well. This is when pH is equal to pKa 2, and that is this condition where we're halfway between those two at exactly an addition of another 50 past first equivalence. And we know the pKa2 in this case is 9.69. So we've actually defined quite a bit of this curve by doing only one calculation that we know how to do really well. And the rest of this, the excess, you know already how to do. The only points that we haven't talked about explicitly are this point and this point, this being the equivalence 2 and this being the equivalence 1, and they're actually pretty similar to what we've done before. So the pH at the equivalence 1 is a little bit more complicated, but we're going to really simplify it for this class. The reason why it's a little more complicated than what we did before is because remember, what I wanted you to think about for the equivalence point is what do you have in solution at the moment you're at equivalence. And so equivalence in this case would be that you have taken the H2A and you've added enough hydroxide that you have completely converted it to HA and water. And so now at equivalence 1, you have these two things in your beaker of water. But for a polyprotic system, this is a little bit tricky. For a monoprotic system, we said, well, you know, HA can just react with water as an acid, and that's all we need to consider. But we know that HA can continue to dissociate here and make this A2 minus as well. And so we don't know whether or not the HA is going to go back towards this direction, because that has some equilibrium, which would be Kb2, and then it could also go this direction in the form of Ka2. And so this species, because it's sort of in the middle of the fully protonated version and the fully unprotonated version, it's not clear to us which direction it would go. And so in more advanced courses like analytical chem, we'll talk about this and we'll think about this with a little bit more nuance. In this class, it turns out that this approximation, we can make a really simple approximation that makes it really simple. And that's a graphical one. So if we look back over to the right at our graph, we can see that this region is nearly flat, which is the buffer region 2, and this region is also nearly flat, which is buffer region 1. So it turns out that equivalence point is always going to lie exactly in the half of those two. And we know where this point is in space, that's pKa2, and we know where this point is in space, that's pKa1, and so this whole thing can be approximated with actually really good degree of accuracy as the pH here, and we'll say that's pH at the first equivalence, is really just the average of the two pKa's, pKa1 plus pK2 over 2. And if you pop those numbers in, that gives you a value of about 6.02. So now we have that point 2 on the curve, and we really did some basic math. All we did was take two numbers, add them together, and divide by 2. And that means we have that point, the 2.34 and the 9.69 we had without even doing any math at all. And so far we've been able to compute every point on this except for the very first one without really doing any math. And to be fair, that math at the first one is something you've done a lot. And so we've actually drawn out the general shape of this thing with all the critical points with the minimal amount of math. And that's what I want you to be able to do in this class, is be able to compute these points, but also very quickly be able to rationalize whether or not they're correct or not because of your intuition. Okay, so the last point then I want to be explicit about is how to figure out the pH at that second equivalence point, which is up here. This is really the outstanding point because we know how to do excess. We've done that a lot. So for this point, it turns out to be the exact same process that you would have used to figure out the equivalence point in a monoprotic system. So remember, for a monoprotic system, we would say, okay, well, what is the equivalence point? That's when you have converted all of, in this case, your acid, H2A, into the conjugate base. For us, that's true, but not only have we converted it to HA minus, we've converted it all the way to A2 minus. So everything we started with as H2A up here is now in the form of A2 minus, which is a base. And what we'd said before when we were talking about monoprotic systems is, well, if it's a base, then it is going to react a little bit with water based on whatever that Kb is to make a little bit of HA plus some hydroxide, and this is going to be dictated by this Kb, and we're going to call this Kb1 because this is the first way that this system can act as a base. And so now everything else becomes nominally the same as what we did before. We just need an ice table. And just like we've done before, we figure out, well, what would the initial concentration of that A2 minus be if it was generated from all the H2A we originally had in solution? Well, we had 0.1 molar H2A to start with, which means we have 0.1 molar to start with here, but we've changed the final volume. And so we account for that here with 0.1 times 100 mils is the original divided by 200 mils, which would be, and actually that should be 300 mils, sorry, because that is the original 100 of the what we had in solution, let's see, up here, plus the 200 required to reach equivalence. So that's the condition. We don't have any HA minus yet, but we will have some after we let it relax, and we have nominal amounts of OH minus. So the rest is all exactly how you've done this before. So some amount X is going to dissociate, or associate in this case, to make X amount of HA and OH minus. We can pop this into the equilibrium expression for Kb. How do we figure out what Kb is? Well, we know that the pKa for the first dissociation is 2.34. The pKa2, that has to do with the dissociation of HA to A2 minus. That was the second step. And so the pKb of the second step, that would be what we would call pKb1. So it's important to remember that these are sort of complementary to each other. So pKa1 and pKb2 must add up to 14, and the same is true for pKa2 and pKb1. So if we took 14 minus 9.69, that would tell us what the pKb1, which would be 4.31. Similarly, we can figure out pKb2, but we don't need to. And if we want to go to Kb, oops, that should be Kb2 here, or that should be Kb1, then we just take the antilog of 4.31. So that would mean that that is equal to 10 to the 4.31, and that will allow us to compute that 10 to the minus, which gives us a Kb of 4.89 times 10 to the minus 5. So now we can use this and solve for X, which gives us 7.1 times 10 to the minus 3. So convince yourself that that's true with the approximation being valid. And this is the X is equal to hydroxide concentration. So to get to H plus, which is what we need to get to pH, then remember we're relating that through Kw, which gives us an H plus of 1.4 times 10 to the minus 12, and then negative log of that gives us this pH of 11.5, which marks our final point on this curve up here. So all the way over here is our 11.85. So this was a nice sort of mix of intuitive determination of points on this curve and some calculation based on our reasoning and deduction of strength of the first acid dissociation and the second. So this is really sort of the penultimate example of putting it all together in your understanding of weak acid, weak base equilibria as it relates to titrations and thinking about something like this.